Welcome back, ladies and gentlemen. We're going to be continuing with balancing chemical equations, but we are going to be taking it a step further. We're going to be working on page 33, types of chemical reactions. If you've been doing your balancing like you were supposed to, which of course you are, you probably noticed that there were certain patterns to things. And remember, we're always about finding patterns because patterns make everything a little bit easier. So what we're going to notice is that certain types of reactions keep coming up. Now, you would have seen this in grade 10, I hope. But the key is always, we're trying to find a pattern of some form so we can work with it. Now, the types of reactions we have is a couple different ones. And I must admit that your notes kind of go through in an order that I normally wouldn't. It starts off with the combustion reaction. The combustion reaction is famous for the fact that, well, broadly speaking, you probably did it to get to school when you actually come to school. Or maybe if you did any barbecuing, you did it. The combustion reaction is when you go something like CXHY plus O2 goes to make CO2 plus H2O. This is a fancy way of saying you burned something. So that, anything that looks like that, is combustion. So if you see some big complicated CH combo molecule and you see some oxygen and you see some carbon dioxide and you see some water, it's combustion. Now, the thing about that CXHY, the reason I put X and Y is because there can be any number of them, right? Like it could be C1H4 or it could be C2H8 or, like there's lots of options. Now, what we're dealing with in terms of this, and this is always one of those little interesting things, is that if you were to toss an oxygen in here, like that, now we're still basically talking about combustion. The difference is we've gone from combusting things like wood and coal and oil to combusting things like sugar and food. This is the same basic cellular respiration that you guys would have seen way back in grade 10 during the ecology unit. Because it turns out that what you do to live is basically burn things. Hence the phrase, burn calories. Anyway, that's sort of the first one. And the example we've got in our book here involves methane and oxygen making carbon dioxide and water. And I ask you to try balancing it. The answers, of course, are located in the drive. The next type of reaction is an interesting one. So this is when you take two small compounds and you make one bigger compound. So two simple to one complex. And you're going to end up with something called a synthesis reaction. And this is usually something like this. What you're seeing here, what I'm writing, is called general reaction types. Okay, so what I'm saying is that two small things, A and B, go to make one complex thing that uses up both of them, AB. So the example that it talks about here is water and dinitrogen pentoxide gas react to produce aqueous hydrogen nitrate. So let's try working with this because we do need a little bit of practice. It says we've got water. Okay, we know what that is. That one's easy. So let's do it in another color here. Let's do it in blue. I mean, we are talking about water, right? So blue. So we've got H2O plus dinitrogen pentoxide. So dinitrogen is N2 oxide 5. Goes to make, what does it say? Hydrogen nitrate. Okay, so nitrate, we can look that up, is NO3. Hydrogen nitrate just means there's an H in front. I'm pretty sure that's in your periodic table, but we'll have to check. Okay, so there it is, and now what? Well, we have to balance it, and we can clearly see very quickly I don't have enough nitrogens. So I'm going to put a 2 right there. 2 times 3 is going to make 6, 5, 6 over there. 2 hydrogens, we're already done. It's finished. There you go. That one's pretty simple. Synthesis reactions are generally simple, but they're important because, well, they make things, a lot of things that we like. So the opposite of synthesis is decomposition. Decomposition is the fancy way to say rot or decay. And what we're dealing with a decomposition reaction is a complicated thing turning into two simple things. So the first one, synthesis, takes two simple and makes one complex. Decomposition takes one complex and makes two simple. You'll notice the way I'm describing it is to help you follow the pattern, because every single one of these chemical reactions is going to be different with different reactants and products, and keeping track of which one is which can be tricky. But if you look for the pattern, it's a lot easier. One complicated, two simple. Two simple, one complicated. If you've got like two complicated ones over here, probably not going to get a synthesis reaction. We're probably going to get something else, if you can remember back to the other times. All right, our decomposition says nickel 2 hydroxide. All right, so nickel 2 hydroxide. Remember, nickel 2 tells you that the nickel has got a charge of 2. It does not mean that there are two nickels. Hydroxide is OH. Hydroxide is 1 minus. Nickel is 2 plus. So in order to balance this, I'm going to need a 2 down there. That's where the 2 comes in. There's always a 2 somewhere. Okay, what else? We're going to get solid nickel oxide and water. Okay, so we're going to get some water, so H2O. You'll notice that it said solid nickel 2 oxide and water, but I just wrote water first. Why? Because it's easier, and it doesn't really matter what order I put them in so long as they're on the correct side of the arrow. Right? The water goes on this side. If I put it on this side, then I did something wrong. But I can put it in any order I want, and I just wanted to highlight that. So nickel 2 oxide, well, we have to figure out what nickel 2 oxide is going to look like, right? This again is 2 minus, this is 2 plus, so they're already balanced, so nothing happens. So I erase my charges. Once again, I'd have to double check, make sure all of this works out. I've got a nickel on both sides, that's awesome. I've got 2 hydrogens here, oh, but I've got 1 oxygen there and 1 oxygen there, oh, but I've got 2 oxygens here. So this one's actually balanced already. We don't have to do a single thing. Now, of course, we are in grade 11. We could be writing down the different states of matter. So, for example, it tells us it's solid nickel hydroxide. So this one here should be solid. And it says that this one here, well, it doesn't say it, but it's water. So it's going to be liquid unless we were doing this particular experiment at like below 0 or above 100 where it would be boiling. And then the last one, of course, it says is solid as well. So there you go. Pretty straightforward. Note the brackets are necessary, and you do need to put it as a subscript, which means that you will have a subscript of the main line. So that's kind of a little weird, but that's how we kind of do it. Computers, of course, have a hard time with that, so it doesn't always look like that. Okay, so that's a decomposition reaction, and I think you could clearly tell that like nickel 2 oxide was pretty complicated compared to the 2 pieces it turned into. Now, the next one is called a single displacement reaction, and this is one in which you did do in grade 10, but now we've got extra rules to go along with it. Why? Because you're in grade 11. You're going to need your periodic table for this one. Well, at least a part of it. So, as it says here in your notes, single displacement reactions are chemical changes that occur when an element replaces a less active element in a compound, leaving the replaced element alone. Okay, so we'll talk about the less active part in a second. First, though, what do we mean when we say replace? Okay, well, it's a single displacement or single replacement reaction. We'll put it over here. A single displacement reaction, which we usually just summarize by saying SD or SR, looks something like this. You've got A by itself plus some complicated BC turns into AC plus B by itself. So effectively what's happening is we are replacing, we are displacing, we are swapping places. The A and the B swap where they are. But in grade 10, we just basically assumed that every single possible combination would automatically work, right? Like it doesn't matter what I put in there, it would change. This is not actually always true. Shocking, I know. Instead, sometimes, like, think about what's going on here, right? A is coming in, B and C are dancing, and A comes in and goes, hey, B, get out. It's my turn to dance. What happens if B is doesn't cooperate. What happens if B says, nah, get out of here? Well, then what's A going to do? Well, not a lot. So if A isn't strong enough to displace B, nothing happens. And we end up with what's called a no reaction. So you put these guys together and nothing happens. There's no cool explosion. There's no color change. There's no fire and light show. It just sits there. Now, we don't expect you to memorize every single possible combination of elements and tell me if it's going to be a single displacement. Instead, that's where this comes in. If you flip to the third page, right, so not this page, but this page, where you've got your polyatomic ions, this side over here is called the activity series. The activity series here basically tells you who is going to replace who. So, ones on the bottom will generally lose to ones on the top. So, for example here, right? Let's take a look. If we look here at our list, lithium is the top slot. So lithium here on the metal side always wins. That's what they're saying. So if potassium was our B up there, right? So if our chemical equation looks something like this, we had Li plus K, we'll make it simple, F. Right? If this was our combo that we started with, lithium is higher in the activity series. It is closer to the top. So it automatically wins any contest. So it will come in, it will kick the potassium out, and you will get your LiF plus potassium, who has to wander off alone and sad to the edge of the dance floor. However, if this was flipped around, right? So let's say instead of it being potassium who originally had the dance partner, what happens if it's lithium who originally has the dance partner? So instead of looking like that, it looks something like this. And potassium shows up late to the party, and they're like, hey, lithium, can I have a turn? And lithium's response will be, no, get out. And that's it. If the particular element is higher on the activity series, it will win, and it will either kick out or stop the other one from kicking them out. And that's it. That's all that you need to worry about that. It's basically an extra step, and what it means is that sometimes the answer to the question is nothing happens, because in this particular case, nothing happens, right? Like, look, this is what I start with. That's what I end with. It's the same thing, so nothing happens. And for these kind of equations where this is what will occur, you can actually write no reaction and call it a day. Question is now done. All right, so let's take a look at an example here that the book gives us, and it talks about fluorine gas react with sodium bromide. All right, so fluorine gas, remember, fluorine is one of our diatomics. It's in the top corner of the periodic table. So fluorine gas is going to be F2, and it's a gas because it's fluorine gas plus sodium bromide, which is probably going to be a solid. I have to check. What does it say? In aqueous solution. I guess wrong. So aqueous solution means that it is dissolved in water. So what it means is that somebody has a beaker, and in the beaker is some water. This is my beaker mug, in case you haven't seen it yet. And in that water is some sodium bromide. So if I were to like pour some fluorine gas in there, yes, you can pour gases. I know it's weird, but you can. Well, it would react. Or would it? We have to check the activity series. If we look here, we see that fluorine is on the top of the non-metal side of the series, which means it will beat chlorine, bromine, and iodine. I know, right? Why isn't iodine? So this becomes to NaF plus Br2. Why is it Br2? Because, of course, bromine will pair up because it's a diatomic. Now, this will be aqueous, and this one here will probably be a gas. It might be a liquid, actually. Bromine is one of the, it says liquid bromine. Bromine is one of only 2 elements on the periodic table that is a liquid at room temperature. The other one is, of course, mercury. So we now have to balance this because we've got 2 fluorines here and we will have 1 here. And we've got 2 bromines and only 1 there. This is really easy to balance. It just looks like that. So there you go. This is a reaction that does happen because fluorine is more aggressive than bromine. We will talk more about why it's more aggressive once we get to the physical properties of matter unit, which is about 2 units in from where we are now. But for the moment, all you have to do is look it up. Now notice, you only really have to do this when it comes to the single displacement. You don't have to do this for the next one on our list, which is the double displacement. The reason you don't have to look it up for double displacement is because both elements are going to switch dance partners, which means it doesn't matter if one of them is weaker than the other, because the strong one will force the weak one out, and then the weak one is going to pair up with whoever's left over anyway. All right, so double displacement, dd, or dr for double replacement. This one is always the weirdest one to write when it comes to doing the general form, because it's going to be AB plus CD goes to make, and this is key, got to pay attention to this, because you don't just jumble up the letters however you want. The first one is the metal. It replaces with the metal of the second one. The same is kind of true up there with the single displacement. Nothing is more hilarious than when I get to watch a student take the non-metal out and put two metals together. Two metals don't do anything generally. That's, like why your phone, so usually I would use an example of a watch, but nobody wears watches anymore anyway, so bad example. Anyway, A and C trade places, which means I end up with CB plus AD. I know, it looks weird. Let's use the example, because the solid concrete example generally makes things a lot easier. It says here we've got aqueous lithium iodide. All right, so we've got Li capital I, and it's aqueous, AQ, plus aqueous silver nitrate, great for dealing with werewolves. It's also AQ. Goes to make solid silver iodide, AgI, plus lithium nitrate. And that is probably aqueous. Let's take a look. Aqueous. Okay, so there it is. And if we take a close look, we'll see the lithium and the silver traded places, just like we said. Now, remember, you're looking for patterns to make this easy. You don't have to analyze in excruciating detail to figure out what type of reaction this is. Just compare how much we had to write for this reaction compared to, say, this reaction. This one here was super simple. This one is not. The less simple something is, the more complex something is, the more it's on sort of this side. These two here, the synthesis and the decomposition, are really, really very straightforward. Usually, if we were in class, one of the things I would do is I have a Kahoot for this very thing, and I would give you about 3 seconds to identify what type of chemical equation it is. And you can do it. Like usually the first couple, everyone panics a bit, but after a little while, you'll get used to it. You'll start looking for key features, because nobody who really knows this stuff is going to analyze every single piece. They're going to glance at it, find the key features that tells them the important information, and just do that. And that's what you're wanting to learn. You're wanting to learn how to be efficient, which is like the good version of lazy. Efficient means that you get to spend more time doing awesome stuff and less time doing annoying stuff. Everyone wants to be efficient. All right, there's one more reaction which you did learn in grade 10, although usually it's done a little later in the unit, which means most people don't realize they're connected. The last one is called the neutralization reaction, or it's called the acid-base reaction. And the acid-base reaction is a reaction between an acid and a base, hence the name. We call this neutralization because you neutralize the acid or the base when you combine them together. This is your classic baking soda and vinegar to make a volcano experiment that you doubtlessly did when you were a little bit younger. Or maybe this summer, because to be honest, volcanoes are cool. So acid and base reaction, as it says here, always produces the same thing, right? A neutralization reaction always produces water and salt. So we always on this side get H2O plus a salt. Now, okay, I should have done this in the right order here. The salt is going to be made with HA plus BOH. So the salt is always Ba. I know, Ba? Why isn't it Ab? Because B stands for base and A stands for acid. And, pay attention, notice the B is clearly a metal and the A is clearly a non-metal. The example that we have in our notes really highlights this, because the example in our notes, let's do it in blue, let's be consistent, is HCl plus NaOH. This is an acid, which you might remember from grade 10 because it's got an H in front. This is a base because it's got an OH in back. And it will produce HOH because the H and the OH will combine, and HOH is another way to write H2O, and our salt. And our salt is going to be NaCl. NaNaB. ClClA. Hence, Ba. So, there you go. That's how you make salt. And this always is a bit of a weird situation because, like, HCl is dangerous, right? If you spilled that on you or drink it, you would need to go to the hospital, depending on how much. NaOH is the same thing. If you got exposed to that in a large quantity and in a large high concentration we'll talk about later in the solution unit, then it would be very dangerous. But water, which is one of the products, you need that to live, and you also need salt to live. Talk about the weirdness of chemistry, right? The individual pieces, incredibly dangerous. Put them together, necessary for life. Just the weirdness of how this stuff works. Okay, so there you go. Those are the different types of reactions, okay? And you can see that they have a certain pattern to them. This pattern, which I am now going to just leave on the board so you can see it nice and clearly. I'll get out of your way. This pattern is what you're looking for, okay? You are looking to figure out how to clearly and easily identify what type of chemical reaction is going on at a glance. Literally, within 3 seconds, you should be able to go boop, boop, and know what it is. And that's it. That should all be all you need. Now, can you do that immediately? Probably not. But with some practice, yeah, you probably can. Okay, so that is page 35 that you, oh no, sorry, that is page 33, 34 in terms of notes, and now 35 is where you can do some practice with this. 36 is predicting products, and realistically, predicting products boils down to this. If I show you something like that, and I ask you, what am I going to make? You should be able to tell me. That's the nature of figuring out these patterns, right? So if you see just something like, I don't know, can I make one up? If you just see CaO arrow, what does that have to be? Well, if you look quickly through the list, it has to be decomposition, because decomposition is the only one that has a single reactant on the reactant side. All right, bad example, Mr. C. You just used that example right there. Let's do something different. What happens if I did CaO plus, making one up off the top of my head, Li3N goes to make. What's that one? Well, it's clearly not decomposition. It doesn't have just one complicated thing. It's not synthesis. Those are both complicated. There's lots of steps here. It's not combustion. I don't see any water, carbon dioxide, oxygen, any carbon combo thing. Oh, this is going to confuse some people who skip around the video. That's combustion. So it's not that one. It could be this one, except that I don't have an A by itself, right? Both of these have got pairs. There's two there, there's two there. So it could be acid-base, except there's no hydrogen or no hydroxide. So it's got to be this one. It has to be this one. It's the only one that even remotely matches. And once you know which one it is, you know how to write what happens. So even though I made this up on the spot, I don't know what the answer is supposed to be. I don't have an answer key in front of me or anything like that. But what I can do is go, well, the rules of double displacement tell me that CA and Li switch places. So I'm going to put CAN plus LiO. Now I've got to balance it, of course. Lithium is going to be 2 on this side because oxygen is 2 minus and lithium is 1 plus. Nitrogen is 3, so I'm going to have to bring a 3 down and a 2 down because calcium is 2. So there we go. Now, of course, we'd have to balance the equation to make it all work. Let's see if I can do this quick. Who knows? This is the problem when you make up a question. You never know if it's going to work well. So that's a 3. This is going to have to be a 3. That's going to have to be a 2. Okay, the 2 there and the 3 there. That makes 6 lithiums, 2 nitrogens, 2 nitrogens, 3 of those, 3 of those, 3 oxygens, 3 oxygens. Yay, it worked. Oh, it's always good. Pressure was on. You guys were watching. That's it. That would be what you would have to do for one of these kind of questions. You'd get some kind of initial condition. You would be expected to put it together, figure out what the product is, balance it, and then you're done. Now, why is that necessary? Because this is effectively the equivalent to being able to write a sentence of your own in English class, right? I've given you the start of the sentence, the beginning of the reaction, and I'm expecting you to be able to finish it. Like, okay, to be fair, it's not the same as writing your own sentence. That's more like writing a sentence after someone gives you a prompt. But eventually, we move towards you writing the sentence on your own. Right? There's a reason I was able to make stuff up, because I've had practice. Okay, so that is what predicting products is. It's very straightforward, really. It's just take the knowledge you have about what's going on and then apply it. Right? And you've only got 6 possible options, these ones here. So provided you keep that in mind and look for the key features, right? Complicated, too simple. It's got carbon and hydrogen and oxygen. Over here, you've got 1 complicated, 1 non-complicated. Here you've got 2 complicated, and here you've got H's and OH's. That's the key part there. So long as you look for those key features, you can identify quickly and then move things around to solve. So that in mind allows you guys to finish up in terms of like the discussion. There's going to be a discussion here in page 36. Page 37, you guys have some examples of predicting products that you can attempt. That's 37. And then 38, 39, 40, all predicting products. So this is a big thing. We need to really work on this. And this is also the last piece of the review. The next page, 41, is about isotopes, which probably not a lot of you guys did. After we finish isotopes and the results of that, we're basically getting down to just 2 more topics. Page 47 is the last page, and we're done the unit. That's it for review, and then we move on to new stuff. So we are very much running out of things to do here, so hopefully things are clicking. Hopefully you guys are able to get things through. I'm going to be having to send off more printing for you guys, although copies of the book are already online in the drive, and you guys can get started on them. So I'm going to leave it there. We just covered everything up to about page 40, give or take, so you guys have lots of stuff to work on, lots of practice to do. Give it a try. Remember, the answer key is located in my copy of the teacher notes in the first folder in that particular unit, right? So it says, step 1, read teacher notes. Hopefully you did that step, because then you'd know that's the answer key as well for all of the practice problems. All right, I've said enough. I will leave it there. Good luck, ladies and gentlemen.